Okay, so we're recording. So what we're looking at here is section 13.1. So chapter 13 deals with vector calculus, and section 13.1 was on vector fields. And a lot of the problems in section 13.1 involve looking at vector fields and trying to match the vector, the formula for the vector field with the appropriate picture. And hopefully for those problems, you won't need technology, but technology is available. So what I've done here is in the folder called MATLAB Programs in your Blackboard, there's a program for the gravitational vector field, okay? And I want you to click on that, and I'm gonna bring it up as well here. One moment. Just give me one moment here. So find that program, please. Let me see, where is my... Just give me a moment here. I'm trying to find my my MATLAB. Wonder why it isn't showing. One moment. Just give me one moment, class. I'm reopening the program again and hoping that the window will show. Yeah, it's coming up. Thank you for your patience. I'm just waiting for the it to come up here. I don't know why it's... Trying to find the window here on my... Here it is. Finally, there it is. Okay, so I think it'll be helpful if I show how I came up with this code. Just give me a moment. I'm going to go to the ebook. Okay, so what this is from section 13.1, where they talk about a conservative vector field. So again, this is a very important, this concept of a conservative vector field. If you have a vector field if you can find a function f if you take the gradient of that function and the gradient of that function is equal to the vector field, you have what's called a potential function f, and the vector field f is called a conservative vector field. Okay, and it turns out that the gravitational field is a conservative vector field. Okay, now what they do, if we go up a little bit here, I got to find example 4. Okay, so in example 4 is when they talk about the gravitational field. And the gravitational field for a vector field, which is a function of the vector x, x is your position in the three-dimensional field, it equals that formula there. What do little m and big M stand for in that formula there for the gravitational field? What do little m and big M represent? Mass, that's right. Very good, very good. Little m could be your mass, and big M could be the Earth's mass, for instance. Excellent. What's the big G stand for? Gravitational, right, gravitational constant. Good, excellent, Charles, excellent, Ian, excellent, Malik, and thank you for also the comments on the last question I asked. So this is the formula for the gravitational vector field. And this formula, we can write out the vector x, okay, and the vector x would, well, the object, they have it right above here. The object, the gravitational force is acting at an object with position x, y, and z. And so, but this is just a compact notation for the vector field. But and notice in the bottom, you have the length or magnitude of the vector x cubed. Okay, so if we were to write out this vector field in a little more detail, okay, this would be our result. So the gravitational vector field, if you write out its components like they show here, okay, they're the components. So like the first component of the gravitational vector field is negative little mass times big mass times gravitational constant g times x divided by x squared plus y squared plus z squared to the 3/2 power. Well, that's like taking the magnitude or of the vector x and squaring it, cubing it, because the magnitude of the vector x is the square root of the distance that the mass at position x is from, say, the origin. The Earth, the center of the Earth is the origin, right? So you have this point or person or whoever that's some distance away from the origin. Well, that person's at coordinates x, y, and z. So the distance then from that person to the center of the Earth, which we could call the origin, would be the square root of x squared plus y squared plus z squared. But if you raise that to the third power, you get x squared plus y squared plus z squared to the 3/2 power. And so that's just the first component. The J and K components work similarly. Are there any questions on this very, like, most famous vector field? I mean, we want to try to tie in what you're learning here to other courses that you've had or you're going to have. How many maybe have seen this in another course, this particular vector field representation for the gravitational field? Has anybody seen that in another course? Okay, Charles has. Excellent, excellent. Okay, well then the question is, you know, what does this gravitational field look like? Well, the gravitational field, you notice that all the components are negative, right? All the components are negative. Okay, the I, J, K components are negative. So the vectors in the field are pointing in what direction? What do all the vectors in the field have to? They have to point. I mean, if you have a person at coordinate x, y, z, and the gravitational field acting on that person obeys this vector field, okay, then how does the gravitational field act on the person? The gravitational field is doing what to the person? It's pulling the person towards what? Towards what? So you have a person standing on the Earth. That's right, Ian. Person standing on the Earth at coordinate x, y, z. The gravitational field is pulling that person towards the center of the Earth, towards the origin. And that's why the components are all negative, right? Because, well, I want to be careful though. You do have the coordinates x, y, and z there, x, y, and z also as part of in the numerator. But the point is, no matter what your location is on the Earth, the gravity is going to act towards pulling you towards the center of the Earth. But we have the Earth, right? And so we don't get pulled in to the center of the Earth, right? And what's this look like now? What's this look like? This gravitational field. Well, so what I did is in the MATLAB program, I programmed these components in. But what I did was I just put in like some values for the the M, the little m, the big M, and the G. Okay, those I mean that determines that determines the gravitational field. You know, it affects the components. But essentially, if I wanted to graph an idea, if I wanted to graph the gravitational field in three-dimensional space, I'm going to have to substitute in some numbers. Okay, and that's what I do. So what I do here is, let me just show you here. Let me go back into the MATLAB. Here's the program. So I choose to have like -5, okay, times x, -5 times y, -5 times z in my numerators. And I'm using what's called point notation. Before every operator, I create a mesh grid of points where every point I'm going to draw a vector. And then the components, well, I have to have dots in front of my operators, like divide and multiply, because, well, like for instance, multiplication in MATLAB doesn't know if you're multiplying two matrices or if you're doing just regular function type math. So, and function type math is point-wise math. In other words, evaluate the vector at this, evaluate the component at this point. So that's why, like for the fx component, I have -5 times x times but I have the dots there in front of the operators. The pluses and the pluses and minuses, you don't need dots in front of those operators. But the times and the divide you do. And then I'm dividing by, you notice all those components, I'm dividing by the square root of the, which is you know, I'm dividing by the distance that the person is from the center of the Earth, and I'm raising it to the third power. Well, also now raising to a power requires a dot in front of the operator. How many maybe have seen this in another class, this pointwise, the pointwise operators? There. Has anybody seen that maybe in another MATLAB class? Okay, Charles has seen it, excellent. And so you know, now you'll notice here a signal analysis, excellent. Thank you, Charles, appreciate it. If I look at this program, you notice I have something called a plus ESP there. Now what that means is I'm adding a very tiny value to my square root in the denominator. Why would I need to do that? And this code might be, you know, new code might not need this, but this code, there's a reason I'm showing you this. Why would I want to have a plus epsilon in the denominator? The epsilon is like 1 times 10 to the negative 21st power, something like that, or one. It's very small. It's a very small decimal. It doesn't affect the value at all. That's right, Charles. The way the mesh grid is, you don't want to be dividing by 0. So this mesh grid is creating coordinates all throughout the XYZ plane. Okay, so like x goes from -1 to 1 with a scale of 0.5. Well, -1 to -0.5 to 0 to 0.5 to 1, 0 is included in there, right? And so you don't want your program to complain because you're dividing by 0. So that's why you have the plus eps there. Okay, so that's just, I think, kind of a neat idea, and that I want to share with you. And if we take the code, here, copy it, and paste it in the command line, and hit enter, we should get a figure. Okay, and let me share with you the figure that I get. Okay, one moment. Let's see, where is it at? Okay, who's getting that figure there? Who's tried the program and got that figure? Okay, I'd like a confirmation from one of you that you tried running the program and got that. Okay, Charles, excellent. Thank you. And anybody else? We're good. Juliana, excellent. Okay, so hey, why are those vectors getting bigger towards the origin? What's going on there? The vectors, the vectors are getting bigger as we approach the origin, these gravitational field vectors. Why would that be? Well, that's right, Ian, but practically speaking, would it make sense that the gravitational field gets stronger as you get closer to the center of the Earth? Would that make sense? Okay, so, all right, thank you, Ian, thank you, Madeline. And so, there you go. Are there any questions on this? Okay, well, so that's, I wanted to share that MATLAB program with you for section 13.1. I'll stop the recording now.